have got Twitter information 2 days before that it has already collected 2 samples and has used the help of Ingenuity helicopter for finding sample-worthy targets. Let us hear from Dr. Swati about the cruise, entry, descent, and landing of Mars 2020, including the new technology that was developed for the Perseverance landing called terrain relative navigation. Now I request Dr. K.R. Suresh Nair, Chair IEEE India Council, to formally welcome Dr. Swati Mohan, Dr. Radhakant Padhi, and other distinguished attendees, including Dr. T.C. Thomas. Dr. Nair, over to you.
Thank you, Puneet. I don't want to take much time. Let us welcome Dr. Swati Mohan for sparing this time, I think early morning, and all the dignitaries, including Dr. Tessita. Thank you and welcome.
Thanks, Dr. Nair. Now I would like to invite Dr. Radhakant Padhi, Professor Aerospace Engineering Department, ISC Bangalore. In fact, he was the man behind organizing this. So, Dr. Padhi, over to you to formally introduce Dr. Swati Mohan.
Sure. Good morning to Dr. Swati Mohan and good evening to all of us here in India. Okay, before I do that, Swati, is it okay to record your session? It's okay? Okay, so we can probably record it. Probably. All right, so I'll tell you a little bit of personal touch. I was actually kind of seeing the mission live on that particular night early in this year. And we are all excited sitting across the world. Of course, I do not know who Dr. Swati Mohan is, but her video is a live memory for all of us in the entire same night. And in my mind, that night itself, I thought, okay, somehow we should have her for a talk in IISc, Indian Institute of Science, for our students, but especially in our department. Then I thought, okay, I mean, if it is now she became like quite popular and she started giving interviews in TVs and all sort of things. And then thought, okay, maybe a lot of people in the entire institute will be interested. So let's have it as an institute seminar, for which our director very, very quickly agreed. Then I talked to Puneet and I told, okay, can we not make it open to Bangalore people as well? And then Puneet told, no, we'll make it all over India, basically, right? So what we started as a small department seminar talk, and then eventually it became all over India Council. We got 2,400 participant interest at least, and then hopefully as the time goes, we'll have at least about 1,000 plus people we are expecting today. And thanks to Dr. Swati Mohan, we also have gone through a little bit of our slides before, and it is going to be a little, both as a combination of kind of popular talk as well as a little bit technical intensive. So that's because we don't want to make it very superficial in that sense, basically. That's the whole idea. I mean, hopefully all of us will enjoy that way. All right, so before we begin the talk, a little bit my duty. Dr. Swati Mohan joined NASA Jet Propulsion Lab, popularly known as JPL, first in 2004 after completing her BS from Cornell University in Mechanical and Aerospace Engineering. After working as a system engineer on Cassini during Saturn orbit insertion and Huygens probe release, she returned back to graduate school in 2005 to MIT. And Dr. Mohan received her PhD and MS and PhD both in aeronautics and astronautics from MIT Space Systems Lab. Since her return to JPL in 2010, Dr. Mohan has worked on multiple missions such as GRAIL and OCO3. Swati has also co-founded and manages the Small Satellite Dynamics Test Bed. For the last 8 years, she has been the lead guidance, navigation, and control system engineer for Mars 2020 Perseverance rover, focusing on cruise and EDL. EDL stands for entry, descent, and landing. For the last years, her role was the Mars 2020 guidance, navigation, and controls operations lead. Dr. Mohan was the mission commentator. Mission commentator. All of us know about it. For the landing of the Perseverance rover on February 18, 2021. He is currently the supervisor of the guidance, navigation, and control system engineering group at NASA JPL. That's a short introduction, and many of our biographies are now documented over Wikipedia, internet, a lot of TV interviews and things like that. So no need to introduce so much formally, but again, all of us will certainly look forward to this and certainly look to learn something from her. And before I stop, I'll also invite her physically whenever she comes to Bangalore to visit us in IISc, which Bangalore happens to be her birthplace, by the way. All of us know that as well by now. Okay. So we'll certainly welcome you whenever it's possible. And before I forget, or maybe we'll forget at the end, so I thought I'll make an open invitation to you to IISc whenever you come. All right, so over to you, Swati.
Absolutely. Namaste, everybody. Thank you so much for having me. It's quite amazing to see the turnout here. I think this is probably one of the largest talks that I've given.
We'll switch off our videos now, and we'll request rather you to keep your video on, and we'll start recording your session. You can share your slide as well.
Sounds good. Let me set up my.
Thank you. Keep going.
Give me 1 second to set up my slides. Okay, good morning, everyone. Good evening. This talk will be a little bit of a combination of history.
It has not yet come, Swati. Just wait a little bit. It has come now. It has come now. Yeah. Keep going.
So this talk will be a little bit about a history of the Mars program at NASA, as well as some technical details about the Perseverance landing itself. So why Mars? You know, Mars has always fascinated people by being the closest to Earth, the closest neighbor, and having features that are very similar to what we see in Earth. Back in the late 90s, NASA started a campaign to formally explore Mars in a very strategic sense. And the idea was to answer some of the big questions of whether or not Mars could have ever had life on it. And these go towards answering the fundamental questions of, are humans alone? Is life only ever evolved on Earth? In order to do this, they set up a series of missions with the objective of following the water. And the reason for this was on Earth here, everywhere that we find water, liquid water, we generally find life. I think there's a statistic that says something like 90% or more of the life on Earth is within 100 miles from some source of water, whether it's ice or rivers or lakes or ponds, you know. So following that trend here on Earth, the NASA set up an exploration architecture to do that same sort of exploration on Mars, to find the water in the hopes that that would lead them to the potential life either in the past on Mars. So Mars sent a series of missions, both a combination of landers, orbiters, and rovers to Mars, starting in the late 90s all the way through 2012. And the object purpose was to find the water. Now, these were very successful, and I'll get a little bit more detail about some of these missions, such as the rovers, in a little bit. But in about 2012, the culmination of all of the missions to date had found the signs of water and found the building blocks of life. So in around 2012, when Perseverance was being envisioned, it was time to go past that next step. So now that we had found the water, we actually had to be able to look for the signs of life in a region where we thought could have been a habitable area. So the strategy changed from not just finding the water to actually being able to find the signs of life on Mars. And part of this is satisfied by Mars sample return, which is to actually bring back samples from Mars to Earth in the order of answering those questions. You know, as spacecraft missions, we can only send so many instruments to do certain calculations to the red planet itself. It's only when we can bring those samples back here to Earth that we can really understand all of it. Now, in order to do this, we decided on a rover. This was not the first rover, it was the next in a long series of rovers. This is a little family portrait of NASA JPL's rovers on Mars prior to Perseverance. So the first rover was the Sojourner rover. It was sent along with the Mars Pathfinder lander in 1997. And Sojourner really was a technology demonstration. Up until that point, nobody knew if it was even possible to drive something on Mars, whether the terrain would permit that sort of wheeled mobility. Sojourner was about the size of a cereal box, very small, and just did short stints from the Pathfinder lander itself. The success of Sojourner allowed us to build the twin rovers Spirit and Opportunity. Sojourner and Spirit and Opportunity were both solar powered. Spirit and Opportunity launched within 6 months of each other. They were kind of built and designed at the same time. They went to 2 separate regions on Mars. What was initially designed and envisioned as a 6 to 9 month mission for these twin rovers has lasted about a decade for each of them on the surface of Mars. And the ability that we were able to do science with that type of roving platform really paved the way for the next series of rovers. So Curiosity, which landed in 2012, was a huge step up from Spirit and Opportunity. What was originally a fairly small, like kid car sized rover, solar powered, short duration, evolved to being a very large roving geologist, about the size of a car with huge suites of instruments, a nuclear power source that would allow it to survive on Mars for a full Mars year. So in being able to adapt the design from Spirit and Opportunity to Perseverance, we had to re-envision the entry, descent, and landing system. Perseverance further augmented Curiosity, and I'll get to that in a little bit. What the entry, descent, and landing system that we had for Sojourner and Spirit and Opportunity was basically a set of balloons that encased the vehicle to protect it from the ground once it fell. So we would come in ballistically into Mars, deploy a parachute. The parachute would slow down the capsule as much as it could to terminal velocity, and then it would lower the vehicle encased in this bubble wrap until it got low enough, and then it would cut the throttle. The vehicle encased in the bubble wrap would then drop to the ground and then bounce as much as it needed to remove all that kinetic energy until it was stationary. Once it was stationary, the spacecraft would puncture the balloons from the inside, let them deflate, and then come out. And the rationale being the spacecraft was small enough, you put enough balloons around it that it provides a really nice cushion. So all of these bounces, it's not hurting the vehicle, and the vehicle is nice and safe at the end of it. Now, when they went from Mars Spirit and Opportunity to Curiosity, they tried to adapt the same design, but it didn't work. Curiosity was so big that any attempt to use this architecture was met with failure. There was no amount of balloons or bubbles around the vehicle that could protect it. The weight of the vehicle during the entry, descent, landing, and the velocities that it was coming down in would end up puncturing and tearing some of these balloons because of the terrain and the different rocks and features of the terrain interacting with that. So they had to envision an entirely new entry, descent, and landing system in order to land Curiosity on Mars. And that's how the Sky Crane landing system was invented. Now, Perseverance inherited Curiosity's entry, descent, and landing system, but it needed more. It wasn't sufficient to just take Curiosity's entry, descent, and landing system as is because of where Perseverance had to go. The mission for Perseverance is to seek the signs of past life and to collect samples that could be one day returned to Earth to be able to say whether or not Mars had past life. Now, in order to do this, we wanted to go to the very best place on Mars in order to collect enough diverse samples that we can make that determination back here on Earth. So the scientists picked Jezero Crater. Now, Jezero Crater, the reason why it's so unique and so special for these questions of habitability is because we believe Jezero Crater was an ancient lake bed on Mars. In this picture, you can actually see the river, what would have been the river coming down, flowing into this set of channels into Jezero Crater, where the crater rim is kind of on this side. This white circle is the Perseverance landing region that we were trying to target. So it's in the lake, in the ancient lake bed itself. Now, these features and why Jezero had been considered in the past but then rejected was because the exact features here that make it super interesting for the scientists, specifically these type of cliffs and ridges and escarpments. Down here is a region of rock fields, basically, that has all sorts of small rocks that would have been what you would see at the bottom of the lake bed. These are the exact features that the scientists like, but for the engineers, they're extremely challenging in order to be able to prove that you could land on a rock, on a slope, on these cliff faces without damage to the vehicle. So Jezero Crater was considered for Curiosity and then rejected because it was deemed not, the probability of landing safely at Jezero for Curiosity was only about 80–85%, and that wasn't enough to guarantee a successful mission, so it was vetoed. For 2020, for Mars Perseverance, what enabled this particular landing site was the new technology of terrain relative navigation. And this allowed Perseverance to actually see, as it was coming down, where it was with respect to all of these hazards and thread the needle between them to find the individual green spots amongst all of these different hazards. And I'll go into a little bit of detail when I talk about the performance of Perseverance landing day. So this kind of sets up why we were going to Mars and what the rationale was for the science that we were going to do there. The Perseverance mission was envisioned right after Curiosity landed, so around 2012, early 2013. And we were given the name Mars 2020, which was a very strict nod to when we needed to launch the mission in 2020. So the mission had 4 main phases. First, the launch phase, 6-month cruise and approach phase, the 7 minutes of terror of entry, descent, and landing on February 18th. And then the surface mission, which is designed for 1.5 Mars years, which is about 3 Earth years. So we did launch successfully. Here are some pictures of the vehicle as it's being buttoned up prior to launch. So I wanted to put this in here because it shows the different pieces of the spacecraft. So the Perseverance rover is actually only one piece. It's this piece right here that's kind of tucked with the wheels up. All around that, all of the different pieces of hardware after that is solely for the purpose of getting Perseverance to the surface of Mars safely. So the first piece up here is the cruise stage. That's a cylindrical spacecraft hardware here with the propellant tanks. The purpose of the cruise stage is simply to get from Earth to Mars. After that, you have the bottom here is the heat shield that protects the whole spacecraft entry capsule, all of this portions from the early atmosphere of Mars and takes a lot of that heat and dissipates it. Then is the back shell, which is this portion here that holds the parachute, which slows down the vehicle to subsonic speeds in order to do the final descent. And then the last piece is the powered descent vehicle, which is basically a set of a jetpack backpack that carries the Perseverance rover to the designated landing target and lowers it on a bridle. So to get sense of scale, this is all of those pieces kind of buttoned up, about to be put in the launch vehicle fairing. There's a set of cabinets back here and maybe a little person back here to get the sense of scale of the vehicle. So Perseverance launched in July 30th, 2020, amongst the global pandemic. We actually had a little bit of a delay, but ended up launching on the first attempt on a beautiful day out in Florida. We had a type 1 trajectory to Mars, which is about the quickest that you can get to Mars. And it was actually a little bit shorter than any of the other Mars missions we've flown by a few days. So this gives a description of the path that Perseverance took from Earth to Mars. So we were about here during launch. We did we had the opportunity to do up to 6 course correction maneuvers, but we only ended up doing 3. We did TCM 1, 2, and 3, and we were quite happy that the targeting for TCM 3 happened to put us where we needed to go, so that we didn't actually need to do the final maneuvers coming into Mars. It was about a 300 million mile journey from Earth to Mars, about 6.5 months. Mars arrival was on February 18th, 2021. So I'll go into a little bit about entry, descent, and landing now, and I wanted to do that by showing the video and talking to it. I think that'll be easier than just going through the slides. So entry, descent, landing was a fixed arrival date on February 18th, no matter which day would have landed on February 18th. The first part of it, about 10 minutes prior to atmospheric entry, is to separate the cruise stage. At this time, we sequence the vehicle and release a series of balance masses in order to create a lift vector. Once we are in the atmosphere, we actually fly it like an airplane, doing a series of S-curves in the atmosphere to control our range once we slow down enough meters per second. So once we're on the parachute, the next thing that has to happen is we have to deploy the heat shield. This is our lens cap that's covering our view. Vehicle goes with our radar designated target straight overhead and lowers the vehicle on vital for it to land over the landing target. The vehicle is over contact and and after this whole process, that's when the vehicle is safely on the surface of Mars and can actually do the entire science mission that it was designed to do. So this same process that I talked to in the video, you can see in this diagram here. So entry, descent, and landing is sometimes known as the 7 minutes of terror because it takes 7 minutes from what we call entry interface to touchdown in order to accomplish all of those different pieces successfully. The one-way light time for the day of landing was about 11 and a half minutes. So by the time we had signal that we had started up here, the vehicle would have actually been on the surface for a few minutes that we just didn't know about. So the entirety of this sequence is done completely autonomously by the vehicle. About an hour and a half prior to entry interface, that's when we turn off the transmitter to the vehicle. So at that point, the ground here at Mission Control can no longer send commands to the vehicle. It's entirely based on the software that's on board the vehicle itself. So to focus on the couple of new technologies of entry, descent, and landing, there are two in particular that I'm going to talk to in a little bit more detail. The first one is the range trigger. So in order to land Perseverance at Jezero Crater, we needed to be able to prove that we could land safely. And there was two aspects of that. The first one was to be able to get a landing region on Mars small enough so that we could assess the safety of that region if we were to land anywhere in between it. And the second one was to be able to thread the needles between all of the hazards in that landing region to land at the safest spot in that landing region. So in order to get the landing region size down, we did a change in code to deploy the parachute based on range to target instead of based on velocity. Curiosity had used a velocity trigger to deploy the parachute, and Perseverance made a change to the logic of that parachute deploy to a range trigger. This allowed us to actually get 40% better performance from that simple one-line change in order to shrink the accuracy by 40% of what Curiosity could do. The second one was terrain relative navigation. This allowed us to actually see the hazards as we were coming down the parachute and select where to go based on where we were at the time of that parachute deploy. So the divert maneuver was always part of the Curiosity heritage, but we changed it to be a smarter divert. So instead of just coming out from underneath the parachute, that divert was used to go to the safest spot that the vehicle could reach based on the fuel that it had. So I'm going to pause here and I want to show another video. And the reason I like this video, even though it's super well put together, is that some of the footage in this video is actual footage from the Perseverance landing. It's not just
propulsion, go. EDL phase lead, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Skycam maneuver has started, about 20 meters off the surface.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
So that video is one of my favorites because for the first time, we actually got footage of the landing, the parachute deployment, the heat shield separation, the view of the rover, and the descent stage as they separated. It was the first time we actually saw it happening on Mars. Before that, we had telemetry. We had ones and zeros of information coming back to say how it should be or what the data says it looks like. But that was the first time we could actually visualize it, to compare it to all this animations and simulations that we'd had to see what it actually looked like on Mars, which was just phenomenal. So here's a little bit more detail about the range trigger that I mentioned. So Curiosity had this larger blue trigger, and you can see that if we had to land in a larger blue trigger, we would have to have more space around that hazard at Jezero crater. So more of the cliff, more of the rock fields, and we'd have to land anywhere in between. So if we were spreading it out between that landing, we'd have to make sure everything in that region was safe, which at Jezero crater just wasn't a possibility because of the cliff face going up on the west side. So what we chose to do is to reduce our region of susceptibility by tightening where we thought we could land. So by changing the decision-making criteria of how we deployed the parachute, we were able to tighten the landing area from the blue ellipse to the yellow ellipse. So the blue is based on velocity only at during entry, descent, landing. That means the vehicle says, when I think I'm at this velocity, then I deploy the parachute. Whereas the yellow ellipse is a little bit more informed. So it uses a velocity constraint range trigger, which means the vehicle says, okay, this is where I need to go. That's my target. When I'm X distance from my target, that's when I'll deploy my chute, but I'll also have some safety buffers so that if my velocity is too high or too low, I'll also trigger just to make sure that I don't, crash in these extreme scenarios. So being able to change that logic from just velocity to the velocity constraint range trigger allowed us to tighten the footprint on Mars by 40%, which went from the red and blue here to the blue and green. So a one-line change of code got us 40% more improvement. The next biggest technology advancement that we did for Perseverance over Curiosity was terrain relative navigation. Now, this was much more extensive than a one-line change of code. It involved putting a whole new sensor on the vehicle, which we call the lander vision system. So the lander vision system is comprised of a whole new processing box called the vision compute element and a lander vision system camera that looks down as the vehicle is descending on the parachute. And what it does is it takes a series of descent images as it's coming down on the parachute and matches them to a map that we've created on board using orbital imagery data from the Mars Reconnaissance Orbiter CTX camera pair. So we put this onboard map onto the computer. As we take images, when we come down, we match features from the image to the map to figure out where we are. Once the vehicle figures out where it is, it uses another map, which is based on the Mars Reconnaissance Orbiter HiRISE instrument to figure out what the safest place is. So we created this hazard map on the ground, the safe target map, and basically marked all of the different hazardous areas on Jezero Crater in varying shades of blue, green, and red in order to distinguish different categories of hazards, whether it's slope or rocks or combinations of the two. And this is what that map looks like compared to the earlier map I showed you just of Jezero. So you can see the areas of the cliff faces are in red, the areas inside craters are red because we can't drive out of those. The rock fields here are in red. So those are the areas that we were trying to avoid. So once we pick a target here, then we can execute the divert in order to get to the safest target that we have the fuel to reach. And that's designated by these white wedges. Those are the areas that we can reach with the vehicle at the time that we make the selection. So we pick the safest spot in one of those, in the sum of those two areas. So the lander vision system, in order to come up with that localization with respect to the surface, has two phases. It has a coarse landmark phase and a fine landmark phase. So in the coarse landmark phase, we basically take 3 images, 5 features per image, and do a batch filter with those 3 images in order to create a single localization, a coarse estimate of where the vehicle is. That coarse estimate feeds the fine phase, where we do a per image estimation using up to 100 images, 100 features per image in order to do the localization. This process was initialized at 4,200 meters from the state estimate that was on board the Rover compute element and needed to work, give a solution within 10 seconds, because that's about the time that we had allocated on the parachute. We had to have the solution prior to backshell separation because that's when we're designing the trajectory to go to the safe target. So we had to make sure that prior to backshell separation, which was around 2,000, 2,100 meters, we had the solution from the lander vision system. In the design of the terrain relative navigation system, we designed the whole system to be able to land accurately to the designated safe target to about 60 meters on the surface of Mars. 40 meters of that was the lander vision system localization accuracy that it was required to do. And then the other portions were the ability to fly out that trajectory and our knowledge of the maps themselves of where we picked the safe target compared to the actual terrain on the ground. So a little bit more detail on the estimation portion. So the reason we needed a new computer on board in order to do this is because the image processing required to do the feature matching is actually pretty computationally heavy. So we designed a new box that used an FPGA to do this processing. So the descent image is the start of the process. In this descent image, we select landmarks, and around each of those landmarks, we create a template, and then that small section is then warped and normalized. The map that stays on board is normalized, and then we use the templates from the image to compare against the normalized map to create a correlation peak. So once we have these correlation peak for each of those, we can put them in an estimator, a common filter, in order to actually estimate the state of the vehicle based on this imaging. So this same process is done in the course phase with 5 larger featured templates, and then it's repeated for the fine phase with 100 templates that are smaller. And by using these templates in an extended common filter, we're actually able to estimate the position, velocity, and attitude of the vehicle. So next, I will actually show a movie of actual landing day of the lander vision system. So you'll see the templates that I mentioned before in these green boxes. So it'll first go through the course phase where there'll be 5 big green boxes of templates, and then it'll go into the fine phase of about 100, 150 of those smaller templates. This square here on the top right is the descent image as it was seen on landing day. The bottom right is the full LVS map that was stored on board. The blue square here shows the smaller region, that's the big left portion. And then the red square is the image footprint normalized on the map itself. So green and blue feature matches these boxes. Those are good. Those were actually the ones that were used. And then we throw out incorrect outliers, landmark matches, and those are designated with the other colors, red, purple, yellow, or orange. So on landing day itself, we did initialize at 4,200. We had a near perfect course phase into the fine phase. So you can see here we have lots of green and blue, which was great. We were able to feature select per nominal as we're coming down on the parachute. At this point, the vehicle is turning over to do the descent. So we weren't required to perform during this. We had already given our solution, but we kept it going to see how well it can do, and it went surprisingly well. So this is the divert tipping over to do the first phase of the divert, and you can see how the features kind of bunch in because of the projection on the ground. And then we've done the divert, and now we're kind of tipping over to slow us down right over the landing target. So you can see how we went from having features throughout the entire region to being focused in on just this one area, which is where we actually landed. So on landing day, our required performance was 60 meters from the selected landing target. On landing day, we actually landed to less than 5 meters away from our landing target, which is phenomenal considering the resolution of the map that we used for localization is 6 meters per pixel. So we basically got sub-pixel accuracy out of the landing vision system. So out of 300 million miles from Earth to Mars, we ended up landing about 5 meters from where we selected to go on Mars, which is just phenomenal. Let's see if I can get. So to close, I'd basically like to reiterate how this process is just an enormous team effort, and the amount of work that happened not just at JPL but across multiple different NASA centers, across multiple different agencies and industry and countries was just huge, of everyone doing their part in order to get to that single day safely. Entry, descent, and landing is so critical that any one thing can cause the whole design to kind of blow up. Any single line of code that's not correct, any one nut or bolt that doesn't work like it's supposed to. So the success that we had on landing day is really a testament to the entire team of everybody who was able to do their part so intricately and flawlessly to put the whole thing together so that it worked. And then this is our final picture, taken about an hour before landing itself, of the team in mission control on landing day that helped land Perseverance on Mars. And with that, I think we have a little bit of time for questions, if there's any questions.
Thank you, Dr. Swati Mohan, for sharing a very, very detailed as well as fascinating story of Mars 2020 Perseverance rover. And we could see a lot of new technologies being developed. And we are having a lot of questions, but before going to the questions, I would like to ask one question from my side. In this mission, why you have not decided to land, but use a kind of a crane and drop the rover? What was the reason behind it?
Yeah, so the reason behind the sky crane maneuver is because the rover itself has a lot of sensitive equipment on the top deck, and there were concerns that if we went straight for a landing, the plumes from the engines would damage the instrumentation on the top, and it was kind of a two-part design, right? Because if the rover was on the bottom and you were coming in, you can't fully land, otherwise the rover would be stuck on the bottom. If you put it on the top, you'd have to somehow drive off, and the designs for that were even more complicated. So they ended up going with a bridle to be able to just keep the rover as is, and the length of that descent stage and bridle was determined so that we could have the flexibility, so we knew that the jets from the plumes wouldn't interact with the rover, and they also wouldn't kick up enough dust that would come back and land on top of the rover to damage the instruments on top.
Well, one quick from my side as well, Radhakanth. What kind of guidance law did you use for re-entry as well as the final power descent? And is it available in some sort of a publication now that some people like us we can look at it?
Yeah, so the guidance, navigation, control design for Mars 2020, and I believe for Curiosity as well, are published in documentations. I know for the Perseverance mission, we published a series of conference papers in the AAS, which is, I think, the American Astronautical Society conference proceedings in August. So that actually does have description of our guidance laws for power descent. I think there was a separate power descent paper versus a guidance, navigation, control general paper.
You can point me to something, right? You can, probably you can communicate over email to get some details about it.
Yes, I can send you the conference proceeding.
Perfect. Okay. Thank you.
I will say that the entry guidance law is actually derived from the Apollo guidance. The same initial techniques that used for the Apollo guidance program were also used for the entry guidance on Mars.
Okay, and how about the final stage, the power descent stage?
The final descent stage, it's basically a polynomial guidance to do the divert, and then a constant velocity hover in order to lower the bridle during that final phase.
Okay, I will look at the publications for more details. Over to you, Puneet.
Yeah, so we are getting several questions. The way questions are coming up, I am not able to pick up one or two, but yes, whatever is there right now, I will read this.
I can try to go backwards here from the chat if you like.
Yeah, that will be better.
Well, Puneet, maybe you can give that option to Swati herself. Let her pick. She can also read the chart, basically, right?
Okay,
Yeah.
okay, sure.
Because we will be selected that way.
Okay, they are definitely coming in very fast here. Let me see if I can answer some of the quicker ones. Parachute is not deployed after attaining terminal velocity. Parachute is deployed around Mach 2, and then we get terminal velocity after that, which is around 100 meters per second. So it slows down after the parachute. What is the most fascinating thing the rover got? I would have to say Perseverance. That's the samples. We've gotten two or three so far, and we're planning to get more, hopefully, in this next region after conjunction here. How long would the program last? So Perseverance is designed for 1.5 Mars years, which is about 3 Earth years. That's under all circumstances. So Curiosity was designed for 1 Mars year, 2 Earth years, and so far it's been 10 years. So fingers crossed that Perseverance has the same longevity that Curiosity has. Do you think that the EDL maneuver of the Sky Crane is perfect and mature enough for future missions, or are you still developing a new, different way for EDL? So the EDL maneuver was really dependent on the nature of the vehicle that's being sent to Mars, right? So the Sky Crane was really good for the large rovers. If we send something else, like a lander, it's not necessarily the appropriate thing to use. So the design of the entry, descent, landing system really is based on what the mission is, what the objectives, and what that vehicle specifically looks like. Where did NASA test this complete landing stage, and how are they achieving Mars-like conditions? There is no way to test entry, descent, and landing as a whole anywhere on Earth. And that's one of the challenges that makes it extremely, terrorizing for those 7 minutes, because we had to do it all piecemeal. We had what we call a trifecta for testing, where we used simulation, hardware testing, and field testing in order to touch all the different aspects, to put them together and hope that on landing day it works. So we use a field testing. We do individual testing on the parachute or on the lander descent system or some on the pyros. Simulations, we did end-to-end Monte Carlo simulations where we varied different parameters like the atmosphere or the landing site or the dust tow, and saw how the system behaved under all of those extremes, in the 99 3 sigma type of percentiles. And then we actually did a bunch of hardware testing with the boxes itself in our mock-up here at JPL with engineering models and with the flight system. And hopefully all those different pieces, you span enough of the space that when you put them together in the flight-like environments, it'll work. Can you explain about the nuclear power systems? So the rover does, Perseverance, and as did Curiosity, uses a radiothermal isotope generator for its nuclear power on the surface of Mars. We did have some solar panels during cruise to Mars, from Earth to Mars, but the primary source is the RTG. What are the plans for the Mars 2026 missions? The next plan is for Mars, is the next step of Mars sample return. So the next mission would be a lander to go get the samples from Perseverance, put them in a rocket called the Mars Ascent Vehicle, and launch them off the surface of Mars, which will be the very first time anyone's tried to launch a rocket somewhere not on Earth. But they'll have to get launched off of Mars and then get captured by another vehicle in Martian orbit. And then that vehicle will have to grab them, leave Martian orbit, come back to Earth, and put them in a capsule, and they'll find another entry, descent, and landing here on Earth. So that's the first leg was Perseverance to pick the samples. The second leg is to get the samples and launch them into Martian orbit, with hopefully the third leg being capturing those samples and then bringing them back to Earth.
And what's the time frame, Swati? I mean, what's the time frame for that mission?
So we're thinking, I think, in the 2030s of getting the samples back to Earth. So I think the next lander to go and retrieve the samples is being earmarked for around 2028, 2030 timeframe. Where does Ingenuity get power while Martian winter is going on? So Ingenuity has solar panels on it and a battery that it uses to get power, similar to how Spirit and Opportunity did. oof. Was the unscented common filter considered as a potential state estimate? Is there any specific reason it was not used? I'm not sure exactly whether the unscented common filter was considered back when we were doing the design. We ended up with an extended common filter for the architecture, and by the time I joined on that TRN task, they had been using an extended common filter for a while through all the prototype demonstrations. So I'd have to go back and ask in the early formulations whether they ever considered the unscented common filter.
So if I can interrupt a little bit, can you put some light on the Ingenuity? We didn't talk anything about Ingenuity.
Oh, so Ingenuity is a little helicopter. I like to think of it, Ingenuity is hopefully.
Do you have one or two slides on that or not?
I don't have slides on Ingenuity,
good.
Sorry. I was just talking about
You
perseverance.
can talk a little bit. I mean, you can talk a little bit.
It is a little helicopter. It is to hopefully future Mars exploration what Sojourner was to the whole rover lineage. So it is a technology demonstration. The entire intent was to see whether you could actually fly on Mars. And the reason that's difficult is because the lift to weight ratio is extremely challenging on Mars. The atmosphere is so much thinner, about 100 times thinner than here on Earth, that in order to get that same lift vector with the helicopter, the blades need to be significantly longer than they would here on Earth. So the material of the blades, how fast you need to spin them to get control, and the how light you can make the target body itself and still be useful was a significant challenge. So Ingenuity was designed as a technology demonstration. It was aimed for, I think, 3, maybe 4 flights at most to prove that you could take off, do a controlled motion in some sort to go to where you wanted to go, and then land safely. It was spectacular achievement. They have done, I think, 14 flights so far, traversed significantly farther, and now have kind of transitioned to being used by Perseverance as part of the science program to go and actually scout regions for Perseverance to inform the Perseverance science team of where they might want to go next. So it's kind of in that transition to actually being a science tool, which is why we had come up with the idea for the helicopter in the first place, of something that could go and scout regions that wasn't limited to what the traversability of that region were, to be able to inform that traversability. I think the questions are coming a little faster than I can read them.
Next is probably one of that I can pick it up. One of my favorite questions.
Sure. Yeah.
Well, I would like to know about the propulsion system for the power descent vehicle and the propellant use. Also about the control system for throttling the engine.
The control system for the propellant engines?
For throttling the engine?
Oh, sorry, could you repeat that? Which engines?
No, also about the control system for throttling the engine. Like, how do you operate the engine?
Oh, so we use actually a series of different thrusters and engines. So we had a set for the cruise vehicle, which was a cruise reaction control system. And then we had one for the descent reaction control system, which was just for the hypersonic aero maneuvering portion. And then we had a series of different engines for the power descent vehicle, which were used for the jetpack landing portion. So the control system, they kind of was in 2 parts. So the guidance navigation control system did enough to determine either the on-off times or the throttle settings that it wanted for the particular engines, depending on which type it was, the cruise, the descent, or the main engines. And then we had a motor controller that actually converted those on-off times or throttle setting to either valve open times or pintle settings on the throttle of the engines themselves.
All right. So next one also let me pick up is one of the students that is taking my course on space dynamics right now. Is the flexibility dynamics of the overall vehicle considered on the Mars atmosphere?
So
About the flexibility dynamics.
yeah, so we do consider the flexible dynamics, and that's one of the things that we have to prove. We do it by phase because the vehicle configuration changes so dramatically in different phases. Like in the entry phase, it's in a capsule, but the power descent is only the power descent vehicle. So we do consider the flexible dynamics in order to prove stability across and gain in phase margin across all of those different regions. Now, some regions and some modes are more were looked at more because of their impact. So there was certain issues, certain analyses that we had to do for like the parachute snatch loads of the vibrations that it could induce into the vehicle due to the different modes and how that got damped out in certain places or how that got excited depending on different isolators we had in the system. While on the parachute also, we had sensors that were on different configurations, like one on the descent stage and one on the lander. So we had to look at the flexible dynamics of the parachute motion and causing the relative state between those two sensors in a dynamic sense. So as a whole, we looked at the flexible modes and made sure that the control system as a whole could control it. But then there was also pieces where we had to look at individual point-to-point transfer functions and specify it to that level to make sure that we didn't excite isolators or didn't saturate some of our instruments, or that the alignments between certain sensors were bounded.
So essentially, it's very, very important to do that in the parachute segment, right? Not necessarily the other segment. Parachute segment is very, very critical for flexibility point of view, right?
Sorry, I didn't quite. It's a little bit muffled, so I didn't quite.
Out of the three segments, like the re-entry or the entry segment or the parachute part or the power descent part, which part is very critical for flexibility point of view? The parachute part, right?
So the power descent vehicle is the one where we were, I think, most concerned with the flexibility. But during the parachute phase, during the parachute phase, we're actually not actively controlling. We open up our dead bands fairly large so that we only control if we absolutely have to. But there, we were more concerned about the flexible modes or excitement of those modes interfering with the sensors. So it was a little bit different than the control bandwidth flexibility analysis that we usually do.
All right. We have now a very young friend who is actually putting his hand up for a very long time. Extremely young friend, Vishwanath. It's all your turn now. Maybe a primary school kid or I don't know, whatever it is. Yeah. Vishwanath, you can unmute yourself and then ask a question. He's holding a little banner to ask you very eagerly.
How does the rover actually analyze the samples, which will collect the data to like to look for bacterial signs of life on Mars?
That's a really good question. So the rover, the sample collection system of the rover has a series of instruments actually that it can use to analyze the sample. So when it first decides in a particular region to make an assessment, it can abrade, basically brush off the rock in that region of where it wants to take a sample, and it can use spectrometers and imaging microscopes to actually look at the region before it takes a sample. Once it actually takes a sample and it's in the sample collection system, it can actually put it has another series of imagers and spectrometers that it can look at the sample that it collected. And there is a way for it to take a bit of that sample, polarize it, and put it into the spectrometer to get some data back as to the composition of those when it looks at it in that chain. But in order to do the full suite of analysis, we really need to bring the sample back to Earth, because we have really great instruments on the rover, but they're finite. There's only a few of them to do all of the different types of analysis, especially the ones that we don't know yet that we want to do until we see certain data. That's why we need to bring it back to the Earth.
Right. One more young participant, again a primary school, Ramesh. Primary school kid. Ramesh, maybe? Ramesh Krishna. Yeah, it's your turn. Unmute yourself. You have identified yourself as an astronaut, probably a future astronaut.
hear me?
All right.
Yes.
My doubt
Yes.
is how long will the RTGs on Perseverance last? For instance, the RTGs on Voyager spacecraft lasted more than 44 years and it's still operational. How long would it last on Perseverance?
We don't know exactly how long it'll last on Perseverance. We hope it's that long. So far, the only sample that we have is things like Voyager, but on Mars, it's the Curiosity rover that originally was designed for 1 Mars year, but now has gone past like 10 Earth years in operation, and it's still going pretty strong. So we're hoping to get at least a decade or maybe 2 out of the Curiosity and Perseverance rovers. We'll have to wait and see how long they last.
Yeah, one more very interesting question from, I don't know, someone probably young again. So he or she is very curious to know, why don't you join ISRO?
I don't know.
Right?
I've never
Why
applied
not?
or been asked to recruit for ISRO, so maybe we'll sometime in the future.
All
Dr.
right,
Swati,
Shout out to my parents, though. My parents are actually in Bangalore right now. They just reached a few days ago, and I think they're on the call somewhere.
Sure, sure. Himansika, you had anything to ask?
Yeah. So, Dr.
Punit,
Swati,
I'm getting that. Himansika, one second. Young people are there, so. Himansika.
Good morning, Swati ma'am. So, my question was, if any hardware is damaged on Mars, so what all measures have you guys taken to take care of that?
Yeah, so that's a really interesting question, and we spend a lot of time on the ground figuring out what we can do. It depends on how it's damaged, right? So we have certain options for power cycling or sending different amounts of power or current through that hardware. We can also dead phase some circuits, which means we can take some circuits out of commission or swap. We have a lot of our key hardware has backup capability, so we can, if there's an issue with one side of the hardware, we can stop using that side and switch to the other. For some of the rover sides on, like Curiosity had some problems with their wheels after driving a lot on Mars. So there's different ways that we can inspect using the cameras on Mars to figure out what the problem is, and then potentially rewrite software to go around or use it in a certain way to not to limit the effect in a certain way if it's being used. So like for the wheels, if they're being torn up by a certain type of terrain, we would have the option to like go around or drive them in a certain way, or drive some wheels more than others in order to mitigate that.
All right, over to Punit maybe. I mean,
so Dr. Swati, there is a question from my side. Just we wanted to know regarding the redundancy philosophy and whether any of the hardwares really failed during this entire process and we executed the redundant system.
So yes, the philosophy was to try to make it as redundant as possible. Now for entry, descent, and landing, it's not really feasible to make everything redundant. So we had single point failures for some things. Like we only had one parachute, right? We only had one radar sensor. We only had one lander vision system sensor. So for some things we did accept that, and those went through more scrutiny in the development phase in order to ensure that it works. For other things like temperature channels or power switches or things like that, those we do have redundancy. And there were instances where we had to use them in the mission. For example, actually right after launch, one of the temperature sensors had an issue. I don't remember if it was like the temperature sensor or the valve upstream or where exactly in the process was, but it caused the vehicle to identify it as a problem and to swap to go into a safe mode. And it for us, it actually manifested that we could see the vehicle, but we couldn't talk to it for a few hours until we had to reconfigure to that setting. So that's one situation where we did actually have a failure on one piece, and we swapped to the backup in order to mitigate that. And once we were on the backup, everything was fine.
Okay. And one more
Yeah,
question regarding the dust storm. Solar cells, because there will be dust storms obviously on the Mars. So how we are taking care when it is on the solar cells, and how we are ensuring that sufficient power is generated?
So when you have a solar cell, a solar panel based rover like the Spirit and Opportunity rovers, we sized the panels assuming a certain amount of dust usage based on the season that it was going in. So for and that's how we designed how large that they needed to be in order to last a certain amount of time, assuming a dust accumulation on the panels. We got lucky with Opportunity, actually, that there was a dust storm, and the effect of the dust storm actually, the wind was enough that it blew off some of the dust on the solar panels. So we actually got a jump like late in life that we didn't expect that allowed it to last longer. But there's no mitigation for that. It comes into the design itself. There's no like windshield wipers on the solar panels that wipes the dust off. We just kind of size the initial to with an assumption of what that dust accumulation would be.
I got a question in the WhatsApp, Puneet. I mean, can I take that?
Yeah, yeah, please.
WhatsApp, he's unable to give it, but he's a colleague from IIT Delhi. And he's asking, will you consider UK for particle filter, something like that, advanced filters in one of your future missions?
Yeah, so the consideration of nuclear power for the vehicle really is driven by what the mission objectives are for the vehicle. If the objective, the reason Curiosity and Perseverance needed nuclear was that they had to last a long time on Mars, right? In order to do the science that they were going to do on Mars, they had to be able to drive long distances and go from place to place and last a long time. Now, different missions have different requirements, right? If it's a landed mission, and maybe it, like for the Mars sample retrieval lander, like the entire objective is to get the samples and launch them. So you may not need to do nuclear power, because if you can show that you can do that in a short amount of time for whatever you can design the solar panels to, then maybe that's sufficient. So the need for nuclear is really driven by the mission objectives and the power consumption to enable those mission objectives.
I see Dr. Tessie Thomas for a long time, so maybe she also has a curiosity to ask you, right? Dr. Tessie Thomas. Maybe. Anything to ask or comment or whatever? I mean, you can unmute and talk maybe. You have to unmute yourself first. Unmute yourself.
Chengappa, I think you have to unmute, madam.
All right, fine.
She can unmute it, sir.
Okay, that's all right.
Okay.
If you unmute it, then she can talk a little bit probably.
No, we have done from our side.
Oh,
Probably ma'am should do it from her side.
Madam, please unmute yourself, then you can talk.
While she does that, I mean, there's another question somewhere. Is there any plan of NASA to send a human mission to Mars? Oh, you are unmuted. You can comment or question.
Yeah.
Whatever.
Okay. It was really amazing, Dr. Swati Mohan, to hear this experience. Wonderful. I think all of us, every word of yours was so interesting. So I was just sitting and hearing you, seeing the questions. Through the questions also we were learning. Really congratulations to you and your team there. Wonderful job for the world. Thank you.
Thank you.
All right, thank you. All right, any other thing, Puneet?
There was a question that I saw come up.
No, wait. I asked a question. I mean, right? Will you ever think about human mission to Mars? Or is it already there in the plate?
So NASA does have some concepts in the works for human missions to Mars. Actually, one of the technology payloads on Perseverance, called MOXIE, was a pathfinder for supporting humans on Mars. MOXIE was an instrument that showed that we could take the atmosphere, the CO2 atmosphere on Mars, and actually create oxygen from it, which is a critical technology for humans going to Mars, because you can't, to send humans, the amount of oxygen you would have to take with you for all those humans for that amount of duration is pretty much a non-starter. If you can create it there, then that makes the feasibility of sending people much more feasible. So Perseverance actually carried MOXIE, and MOXIE was also one of the demonstrations that went very successfully right after landing. So it showed that it could, I may not be getting the numbers correct here, but it showed that it could successfully create oxygen from the carbon dioxide environment. And the purity, I think, of that, the oxygen that created was extremely high. It was like 99, 95 point, which was one of their main objectives that they were able to cross off. So that kind of one example of how we're trying to push technologies for eventual human exploration of Mars. I do see another question that keeps coming up of how computer vision plays a crucial role in the path planning for rover navigation. There are two aspects of that. So we use the computer vision as part of the lander vision system to localize with respect to Mars during entry, descent, and landing. But that same computer, the vision compute element, is actually used on the surface to do autonomous navigation. So on the surface, we use cameras on board to take images as we drive, and basically do a correlation, computer vision, between the first image and the second image to be able to determine how far the vehicle has moved in that time step. And then that feeds into the autonomous navigation part that does uses imagery to do a mapping of the area and create the hazards, and does a path planning of where to go, how it needs to get to its target by traversing all of these obstacles. So the computer vision, as part of that, allowed Perseverance's autonomous navigation system to be significantly faster than Curiosity. So Perseverance, I think, is around 100 meters per hour, whereas Curiosity was about 8 meters per hour. And part of that was because of the computer vision we put on the vision compute element that allowed Perseverance to image and think while it drove, in order to create the paths and the steps and figure out how far along the path it had gone.
All right. So one more person waiting for a long time. I mean, there are a lot of hand-raising questions, and we just can't take everyone, basically, right? But Mukti Prada, maybe you're waiting for a long time. Mukti Prada?
Yes, sir. Thank you, sir. So my question was, the physical samples that are collected, I assume that it's just finite amount of physical samples that can be collected, right? And those samples will be bought back, as you said, like 2028 or 2030s, it will be bought back. But there might be a situation where the rover finds some more samples which are really important and it doesn't have a space to collect it. So is there a system where it stores the data that this is the place where you have to go get the collect the sample because this is important later on? Is there any system like that?
So the rover does have, in the surface mission concept, it does have a depoting capability, which means it can drop samples. So let me preface that with the number of samples that Perseverance can collect, like the number of actual sample tubes it has, is greater than the number of samples that can fit in the sample return canister, right? So it will go along and collect samples in its lifetime, the next 3-4 years. The next mission doesn't go till 2028, so there's a window to be able to choose, right, of all the samples it collects, what are the ones that we want to actually be in that first round of sample collection. So in order to do that, part of what we have designed is to create depots on Mars of where Perseverance will drop those samples for future collection. So it'll drop those samples where we identify those regions on Mars so that we know where they are, and then the next mission can go and get them. So Perseverance does have the capability to do multiple depots on Mars, not just maybe one where the next mission will go, but another one also if it decides to. And that's the selection and the depots. That's kind of will all be decided later as we collect these samples and figure out the nature of each sample or what region it does, and like how to best bring the diverse set back to Earth.
All right, one more interesting question out here. So, I mean, and now that you have spent a couple of months already, was there something really good that we found in this as part of this mission already?
Are you talking scientifically?
Right, right.
Yeah. So scientifically, the scientists, and I have to admit, I'm an engineer, not a scientist, so I haven't been keeping into date with the actual science communications, but I do know that they're quite excited about the different features that they see on Mars. The first sample that they tried to collect was from a rock that was from like an ancient riverbed, and they thought it was going to be one way, and then they went and collected it and it behaved a certain way. So they're like, oh, this is new, and trying to figure out what that meant in terms of the sediment and stuff in that rock. So there's always things that come up that surprise you on Mars, and they're just like previous landing sites. Curiosity and Spirit and Opportunity, Perseverance is finding that too. So each of these new regions that they go to are kind of informed by the discoveries that they've made in the last one. Actually, they just released Perseverance is on the cover of Science magazine. So there's a whole article in Science that was just released about the discoveries that it's made so far.
One more crazy question. I mean, I will put it as a crazy question anyway, but then no question is crazy, right? I mean, so somebody asked, okay, how long will it take for NASA to build a vehicle which can travel at the speed of light?
I'm going to defer that because that, I don't know how to answer that.
All right, over to you, Puneet.
Yeah, so I think we have already overshooted our time by 20 minutes. And we are having, I know, if we will continue, it is another 2 hours we can continue.
It was up to 8:30, Puneet. It's not, I mean, we agreed until 8:30. So.
I think we have 10 more minutes.
Yeah.
Okay, so I think.
So I'll take a technical question. And again, one of the student who is taking my class right now. And what kind of axis frame did you use? Which kind of axis frame? I mean, whether the frame of reference changes on landing for navigation and guidance during the entire sequence. Could you please elaborate how it works?
Yeah, so it was my job to actually maintain the landing, the entry, descent, landing reference frame document. So I had to, make sure I created all those, said what they were used for, when they were used, by who they were used for, and update the frame based on the final measurement to create them. So
what are those frames? Sorry to interrupt you. What are those frames? Are they like local inertial, or the LDLH, or are they? I mean, what kind of frames you use?
We use a lot of different frames, and we use them, for different things. So the vehicle itself controls what we call the descent stage frame. So that's fixed to the body of the rover, body of the descent stage in a particular configuration. That's the origin and body fixed spacecraft frame that we use primarily for entry, descent, landing. We also use what we call a Mars surface frame, and that is defined at surface acquisition during entry, descent, and landing. And it's a surface relative frame that allows us to say where we are with respect to the ground and where we need to traverse to the landing target. In addition to those, we use things like MCMF, Mars-centered Mars fixed frame, to define the orbit of the planet as we're coming into it. We use frames that are fixed to our different sensors, like on the IMU, on the Land Vision System camera. We use on our radar in order to take the sensor frames and map them back into the descent stage. We have gravity frames that are fixed to the landing site itself to understand how the gravity field changes over the over the landing ellipse region. We have frames associated with our actuators. You know, we have frames all over the place, and the maintenance of those frames is really critical to make sure everyone is, you know, using the same assumptions of all of those frames, and being able to translate between all of those different frames.
This is something I keep on emphasizing in my course. I mean, as an aerospace engineer, you should love the axis frames and the transfer of that information between each of them.
Yeah,
And without that, there is no aerospace problem you can do.
We have to take from inertial frame J2000. We go from J2000 to Mars centered, Mars fixed, Mars centered, Mars fixed to the propagated frame from our initial position. From there to Mars surface relative frame to the descent stage frame to the finally the rover frame on the ground. So there's a huge series of handoffs as we change algorithms depending on where we are in that landing process.
All right. Can another lander supply the tubes of perseverance at the time of samples return? So that at the time of sample return, so that it gets another set of tubes in continuous collection. I mean, I don't know. Did you get the question?
I think the question is like, can the next mission go and give more tubes to Perseverance to use?
Right.
I don't know if that's the case. The tubes that we have on Perseverance, they had to be specially designed and verified to be extremely clean, and they are contained within the belly of the rover that we then take out in order to take the samples. I don't know if there's a mechanism to get them from the outside and come in, because the way that the sample acquisition happens, it happens with the tube and the drill bit at the same time. Now, that being said, you know, we have a bunch of super smart, crazy engineers, so maybe, I mean, depending on what you could fix to the other rover, you never know. But it wasn't designed with that requirement in mind. It was not designed to take a up supply of sample tubes.
All right. Should we continue, or so it's time to kind of give closing remarks?
Yeah.
It's very hard question, I know that. Still.
That's what I was telling. If we want to continue, we can continue another 2 hours, but at every good thing has to end. Yeah, I think Dr. Thomas is having some questions. So, madam, over to you.
Ma'am, you need to
One
unmute.
query, like did for the whole mission, did we have any communication blackout?
During cruise, we did not have communication blackout, but there are certain key portions of entry, descent, and landing where we do experience communication blackout, and those are somewhat expected due to high dynamic events. So we did have a short communication blackout during entry, what we call a plasma blackout, when the entry vehicle is going so fast that the fluid around it becomes superheated, and basically that fluid is going around the antennas. So antennas, you just can't, it's basically absorbing the transmission via that. And then we have momentary blackouts as we switch antennas. In order to do entry, descent, and landing, we have to go through like 3 or 4 antennas throughout the mission, just because of the dynamics of the pitch over. So when we switch between those antennas, we did have gaps in our telemetry. And then there were certain configurations of entry, descent, landing. We didn't see this on actual day of landing, but in some of our simulations, depending on how late it went or potential different landing sites, we could have seen some blackouts due to terrain effects as we were coming in, of depending on the angles that we were coming in. We didn't actually see those on the day of landing, but they were something that we considered too when designing.
Yeah, one more curiosity, like all those videos that you showed, those videos were actually kind of generated in a simulation, or somebody was actually taking the video somewhere?
So the first video I showed was an animation based on data from one of our simulations. The second video that I showed, most of the video in there, like the parachute deploy and the rover and the heat shield, those are all footage from the Perseverance landing itself.
Oh, really? No, no. From a distance, you saw that, right? The shock wave getting generated, and then those things, basically, right? From a distance.
From a distance, those are animations that the JPL graphics makes.
Maybe based on the telemetry data, you superimpose that and generate those, right?
That particular one, the one where it's streaking across the sky, I think that's just an animation.
Right.
We had others that we used for landing day visualizations that were based on telemetry itself.
Got it. All right. I think, as Puneet rightly told, every good thing should come to an end. I am very sure a lot of them will be disappointed. Last question. All right, fine, why not?
Thank you very much, sir. Ma'am, what kind of navigation system used in the Perseverance rover, ma'am? Like, what kind of navigation system has been installed?
On the surface for the rover navigation, or during entry, descent, landing, or cruise? Which one are you referring to?
During the en route and the landing at the last moment, what kind of the navigation used for measuring the landing, ma'am?
So the navigation that we actually flew was based on the radar and inertial measurement unit. So the radar was providing the range and velocity, and the inertial measurement was providing the accelerations and angular velocities, and those were fed into a filter that measured the state vector, the position, velocity, attitude, and that was used to control about the landing target, which was created at the time of back shell separation down to the sky crane hover distance, and that trajectory was followed by the navigation filter.
Okay, ma'am. Is there a camera also used for the measuring the landing surface, ma'am?
So the camera was only for Perseverance. The camera was
I think the voice is lost, right?
I think, Swati, we lost you.
Oh, somebody muted me. The camera was only used once to create the localization while on the parachute. It was not used to inform the navigation state after that time. So after that, we only flew with the radar and the inertial measurement based state estimate.
All right. Very interesting question. We have a lot of water over here. Why do you want water in Mars?
Well, if you want it, water here is where you find life. So if you find water on Mars, then you find life. If you find life on Mars, that's huge, right? That means Earth wasn't the only place where life existed, and that fundamentally changes how we think of ourselves or what the possibilities of life elsewhere in the universe are. And that's massive change.
I think, we've come to a very long session, conclusion of a long session. A very long, and a lot of questions are still there. Probably they can they can trouble some of us now that they know that we also have some interest out there. And we can continue to have association. And I repeat my invitation to you: whenever you find time to come to India, do make a point to come to your birthplace. I will be more than delighted to have you here, and then we'll probably have some intellectual sessions again. All right. So with that, we'll probably have the final concluding remarks from both Puneet as well as the IEEE India Council chair, Dr.
So
C.S. Nair.
first, I will like to hear from Dr. Nair. So, Dr. Nair, over to you.
Thank you, Puneet. That was really interesting talk. You can see that from school students to the live members attended this one. I think everyone enjoyed. We could have continued this with questions for maybe another 2 hours or so. So that itself shows the interesting subject. How interesting it is, and we would like to thank Dr. Swati Mohan for sparing her time. Thank you very much. And also, we would like to thank other dignitaries, including Dr. Tessie Thomas and also Professor Padi, who has taken the initiatives to, take this discussion forward. And thank you, Puneet. And we would like to thank all the other attendees. Thank you very much.
So thank you very much, Dr. Swati Mohan, Dr. Tethi Thomas, and Dr. Nair, and of course my co-host Dr. Radhakant Padi for organizing this wonderful lecture. And before wrapping up, I would also like to place on record the help rendered by Mr. Chengappa because this entire mailing list of 2,400 was managed by him, and we could not send from a single mail ID, so he created multiple mail IDs to send the details. Still, there were some issues, but with all said and done, it was a really a fantastic webinar, I can say, which we could get from Dr. Swati Mohan, and we have got a lot of interesting information about the entry, descent, and landing of Mars 2020. And I hope in India also, I can see there is a lot of participation from ISRO as well. So because they also want to know how NASA is working in these technologies. So I can see quite senior, including Associate Director of IISU, as well as Deputy Director of our URO Satellite Center. So multiple very, very senior distinguished dignitaries are already there to hear these talks. That shows that how much interest we have created by inviting Dr. Swati Mohan in India. And yes, this pandemic is a blessing in disguise, because if we would have done a physical event in Bangalore, we would have not got this much participation. And but now sitting in US, you are talking with us, and we are having people joining from across India. So that shows that we were really successful in organizing this webinar. And I would like to also announce that this will be the last IC-PACE webinar for this year. And with this, we will be closing this webinar series on a very high note. And I can see our chair-elect, Professor Devabrata Das, is also there. So before closing, I would like to invite him for his closing remarks. Professor Das, over to you.
Thank you, Mr. Puneet, for arranging this such an interesting talk. And talk was excellent. And moreover that, the question answer session was very nicely addressed by Dr. Swati Mohan, and such a wonderful and down-to-earth person, humble, so which interests the school kids to ask questions. So nice of her. Thank you, Dr. Swati, and thank you, Professor Padi, for orchestrating the questions so nicely along with Puneet. Thanks and namaste.
All right, thank you all. See you.
Thank you, one and all. Thank you very much for joining us.
And probably the recording will be available in the YouTube. So probably some of you can see that recording as well.
Yes,
Thank
yes.
you.